SwayamPrabha. Digital India. Educated India.
Come back. So we're going to start looking at the fundamental equations of motion, which is continuity, momentum, conservation of mass, momentum and energy basically, right, when applied to a turbulent flow, right. That is what we had started out doing. So, let us go ahead and do that. Before I sort of delve into that, just I am going to write out a few mathematical entities which we will need as we go along when we do the math, right, because we are going to insert the definition of a turbulent property into the fundamental equations of motion as we discussed previously. So, in that context, right. So, this is just a math part and I am going to just write that down. So, for example, we have say these quantities which we are going to use for turbulent flow. So, let us just say we have two quantities F and G, and these are just some arbitrary quantities. Now, this could be, for example, U and V components of the velocity. It could be that as well, right. Okay. So, then these are some of the expressions which we will need, right. The mean of the prime, okay. And if you sort of say is the u velocity, just think about this, what it should be, whether it makes sense or not, okay. Then okay, then F then just a minute. Okay. So, F dash G bar, right, that is also equal to 0. Okay. Then okay, then okay. The proof of this, of course, there is proof of this, but I guess I am not getting into it, right. It's beyond the scope of this class, and I think you can just be able to look up this mathematics in some very standard basic book, right. Okay. Right, and you take a mean of that, which is also equal to the mean of. That is all. So, these are some of the quantities which some of the expressions which we will need. Okay. All right. So, now let us move on to the equations and let us see what we will do. Now, previously what we have essentially said, right, is that for a turbulent flow, this is the velocity profile which I had written in the earlier case, but incompressible for turbulent flow. I'll just write that down one more time, okay, to remind ourselves. Okay, so we did write this incompressible fluid flow, right? So then that is this right. So now for example, if you have the continuity equation, right, which is so for example, you have the continuity equation. What is the continuity equation? Right. So this is essentially I'm going to call this as 1. So this is what we have known so far, right? Now, how does this continuity equation change or account for turbulence? I mean, this is an equation. If you solve, you're going to get u, v, and w, which is this, right? Which is essentially this u, v, and w, right? However, using this if I do find out what the values of u, v, and w, do I have sufficient information available to me where I can actually write it in this form, right? So, this is my understanding, right? This is my understanding or how I want to describe a turbulent flow, where I take a mean flow and add a certain fluctuation to it, right? And then these are functions of space and time, all of these quantities. Right. So, essentially my job today right now, I mean right now in these equations when we deal with this, the u that you see here is exactly the u which is here. So, essentially what I am going to do is do that. This is my definition of what turbulence is, which reflects what is turbulence. We saw pictures of that, and after that we were looking at a few things, how we can write the velocity. Now we are actually boiling down to the point where we can actually calculate that what is a minimum or a mean value of the velocity that the flow maintains, and then oscillates or randomly oscillates or fluctuates across this mean, right. So, which is that defined by these primes, right. So, mathematically it boils down to writing out the components of velocity, which is the u, v, and w, which is right here, as sums of means and a prime, right. So, that's exactly what I'm going to do right now, okay, and then see where this sort of takes us, right. So, what can we do if I look at this equation? So, this is the continuity equation. What can I do? Now, first thing I will do is take a time average. I'm going to take a time average, and then if I do that, essentially, so I'm going to say I take a time average value of the continuity equation, which means right. Is that right? Okay. So, now okay. So, this if I take a time average, it's like that, right. So, then we do this, okay. So, you have equation the expression 1 here, right, and expression 2 here. This is the time average. Okay. Now, what we will do is we will subtract the second equation from first, right. I subtract the second equation from the first, meaning subtract this, right. So, what you have because of that. So, what you have now is that right. Right. What is this boiler? So, if I do that, then what do I get? So, u minus u bar, right, and v minus v bar, etc. So, if I do that, if you look at these, so u minus u bar is nothing but u dash, v minus v bar is nothing but v dash, right, and w minus w2 is nothing but w dash. So, therefore, u dash right, and this right. So, this is an okay. So, so I have equation I have expression 3, right. So, I have expression 3 and I have expression 2, right, and of course, I have expression 1. Now, what is this telling me physically, right? What is this telling me physically? So, first the equation 1 here, the expression 1 here is basically telling us that the velocity satisfies continuity, right. What the second one is telling us that the time averaged of the velocity also satisfies continuity, right. And what this one is telling us, the third one, is that the fluctuating components of the velocity of a turbulent flow also satisfy continuity. Is that right? So, I think we should write that as a statement here. So, this is basically telling us that both right mean values and the fluctuating so both the mean values as well as the fluctuating components of velocity satisfy continuity. Is that right? It satisfies continuity, right? Okay. So, now having said that, let us now move on to, so that's about continuity. So, now the next thing is we are going to move on to the Navier-Stokes equation and see what sort of math will be involved in terms of the using a turbulent flow for its analysis, right. Okay. So, that's that then. Okay. So, next thing is nonlinear Navier-Stokes equations. Okay. So, nonlinear Navier-Stokes equations. Okay. So, let me write that down first. Okay. So, that is right. Right. So, I am writing this without any vector notations. So, essentially, we're just doing that, right. This whole thing becomes a vector and this, right. So, here, so essentially the left hand side is rate of change of momentum and the right hand side is the gravitational force, pressure force, viscous force, right. That is what the Navier-Stokes equation is all about. Okay. So, if I do that, right, or dividing by rho throughout, okay, what happened to the rho g? Well, we just say that we are going to ignore the, so let us just say we shall ignore gravitational forces. Okay, so we ignore the gravitational force. Okay, so then that right. So, this is the kinematic viscosity, right, and or is the dynamic viscosity. So, we divide by rho and then we get this. Okay. So, all right. So, this is my Navier-Stokes equation where we ignore the gravitational forces, right. So, and that is that. Okay. Now, so this is a velocity. So essentially you could think of this, so rate of change of velocity, which we see on the left hand side, right. But this is something you could also use for any other property, for example, any other physical property, for example, say density or temperature. You could also do that as well. Okay. So anyway, let us start with, say, velocity, as usual, let us say we have a velocity okay. So, let us just say we have a velocity where we have the three components, right. This, and we shall for a particular case we shall consider the u component or x component or I component of the velocity. Is that right? Okay. So, if I do that, then what shall we get, right? If I do that, then what do I get in the sense if I use it over here, right? So, then in that case, there are two things here. Okay. We will take the then this will mean and we have spoken about this. So, now you have to remember this. So, du dt, this is something which I will write out from the this expression du dt is essentially what we have here, which is nothing but Navier-Stokes equation. So, if I write out like that, essentially taking u in the place of the v here, right, this is a total velocity. So, then what I get here is Is that right? Okay. Now, this is also equal to, this is the total derivative or material derivative, right. So, this is also equal to right plus right. So, why is the left hand side equal to this? So, essentially instantaneous change in the u component of velocity or x component of velocity and the change in the velocity due to its movement, right, in the and due to its movement. Okay. So, the fluid is moving in a certain direction, and because of which it is the fluid which is moving, which has a velocity capital V here. Right. So, I am looking at the changes in the velocity. So, whatever directions of velocity that the fluid is moving, in this particular case, it is important to note here. So, the fluid is moving in the x, y and z direction. So, because of this total movement in the fluid flow in a 3D domain, what is the change in the velocity u component? Right. So, u component of velocity is the component of velocity in the x direction. Right. The movement, however, is happening in x, y and z directions. Right. So, what the convective term here is looking at is essentially the change in the velocity u component of velocity due to the movement of the fluid, and hence we have the capital V there, right, which is essentially denoting the total velocity. Right. So, therefore, the total derivative on the left hand side looks like that. Right. Total velocity looks like that. Now, then let us see. Now, we are slowly getting into details of this. Now, let us now look at this term V dot this, right, del. So, what is that? So, that is, let us just say, will be equal to, you can find that out, right. So, let me write it for you once, and then you should be able to do that without writing also. This, what is del? This, right. So, this is nothing but, therefore, I can write this as is that right? So, you get that. So, then you have something like this. Okay. Now, so this is almost like it's it's almost like an operator, this V dot. Now, then what happens to the term this, right, the second term, basically the convective term. So, you see how mathematically this gets a little slowly gets a little complicated. All this is doing, all we are talking about here is basically the fluid moving, and because of that there is fluid moving in space. So, physically the fluid is moving, and because of that there is a change in the x component of velocity. But when we write it down, it becomes a little more complicated, although it is that simple. It is just a convective change in the x component of velocity. So, what we first did is V dot del, so which is this, right, and you get that, right. So, therefore, right, then the second term becomes into u, right. So, if I do that, V dot into u is nothing but correct. So, therefore, this boils down to this equation, this expression. Okay. Can we write something else to this? Can we write this also in another form? Can we do any other change to this? Right. So, can I also write this as, for example, this? Right. So, UW. So, can I just write it like that? Right. So, let us just say this is from a math point of view, and yes, I can actually write it. So, I am not going to put this down as a formula. What you see here is that yes, I could actually write this down in this fashion. Okay. Now, if I do that, okay, then let us take a time average. Let us take a time average of right. So, therefore, I have and a time average of that is equal to a time average of that is also a time average of that, right. So, now we shall use the expressions which we had used, I had written out right at the beginning here. Right. So, I had written out these expressions. So, these are expressions that one will, I'll just going to sort of pull up and use it in this case, right. So, when I do this, what can I write? So, this is equal to this right. So, this can also be written as, again, this is just the math, and I have okay. Okay. That, okay. Then similarly, so we will have time average of right this. So, again okay. So, of course, you can see that I can write this as del y u dash v dash this, right. this. Right. So, I can write that. I basically am bunching up, the first terms in I'm bunching up the first terms in the brackets here, these 3 terms into here, and then I'm writing out separately the second terms out here. Okay. So, if I do that, okay, and of course, this is the this, right. Okay. Now, again, so let that be. So, we will just leave it at that. Okay. Then again, what we had written out as the total derivative, right. So, v dot del is something that we have written out as above. Okay. So, if I do this, and here also we should take the time average for this. Okay. So, taking time average, right. If I do that, okay. So, again, so let us see if we can write. So, if I do this, right, taking time average of the expression for total velocity. So, if I do that, then okay. So, v dot del into u. So, that's exactly, we take the time average of that. So, if we take the time average of that, okay. Okay. So, if I do that, right, so I am going to take the, okay, so this, and then we take a time, yeah, this is just something that we have written out right here. We have taken out right here, we have written out right here. Okay. All right. So, now okay. I am just writing it out as we have written just now, that is all. Okay. So, that is the no, okay, just have gone to the next page. Okay, making too many mistakes. Okay, fine. So, we will leave it at that. Okay. So, if I take time average, I can write out the expression for this, right. So, now so essentially what I did is I looked at this equation, right. I looked at this equation and each of these terms here, right, that is what I have written like this. So, this term is actually the same as this, right. So, therefore, I am able to, when I write this, I take this one u bar over this, it is the same thing. You just, when you do this, you just take a derivative in the x direction on the mean velocity. Okay. All right. So, so that is that. So, if I do this, right. Now, if I do this, right, now look at this term here in this expression. Now, look at this term or these group of terms. Do they make any impression to you? So, right, if you see this, right, this is the instantaneous derivative of the mean velocity. This is u bar del u del x, v bar del u bar del y, w bar del u bar del z. Do these terms together mean anything to you? Is it ringing a bell? So, essentially it is an instantaneous change in the mean velocity and also convective change in the mean velocity due to the mean flow. So, therefore, the flow of the velocity that we are considering now is the mean flow and hence we have these components which is u bar, v bar and w bar, right. So, this is a change in the mean velocity that we are talking about. Okay. So, therefore, this is something I can also write as d mean dt, right. I can also write it in this fashion, right. So, therefore, essentially what I am talking about here is so the first term boils down to this, right. This, right, plus of course, we have take a mean, that take a mean. Is that right? So, the first term again, so left hand side is okay, there is a small mistake here. So, what is the difference between, so this is important here, what is the difference between this and this term? So, this term is essentially the total derivative of the mean u component of velocity, right. So, total derivative of the mean x component of velocity. What this is essentially the mean of the total change in the u component of velocity. You understand? Let me write that down. So, what the left hand side here is, mean of total derivative or material derivative So, mean of total derivative of x component of velocity, right, and what is this? This is total derivative x component of velocity. So, this is the total derivative of mean x component of velocity, right, and the left hand side is essentially mean of the total derivative of x component of velocity. That is the difference. Okay. So, as you can see, I can also write this for the y and the z components of velocity. So, let us do that. Okay. So, this is one component that we wrote down. So, what is this thing that we are writing? Well, this is nothing but the Navier-Stokes equation, but now as you can see that I have mean components going on here, I have fluctuating components going on here, I have time derivatives going on here, of time derivatives of individual components of velocity as well as derivatives, right. So, I can also write similarly for the y component and z components, right. So, which is basically, let us just say, and the mean is equal to right plus mean and mean components. Okay. Similarly, for the z component, time average and time average, right. So, if you see that, so these are the three equations, right. Now, so if I say if I'm able to write it this way, then shall I write in therefore shall I write dV this, just put a notation there, right. So, I is also equal to, so I is equal to 1, 2, 3 and j is equal to 1, 2, 3 as well. Is that right? So, you can cross check if whether this expression is correct or not, how, and so that we get back the equations that I have written above. Yeah. Okay. So, we can let me do one cross check. Okay, I'll do one cross check. So, if I do a cross check, you need to do this yourself and make sure that you get back the equations. Cross check. Okay. So, say I is equal to 1, right. Then for that j is equal to 1 to 3, right. So, therefore, well, yeah, since I am not writing it. Okay. Okay, I should have written that there. I was missing out the mean. So, that is that. Okay. Plus, so we will essentially have 3 terms now for the second term, where I is equal to 1, but j goes from 1 to 3. So, what we will have here is, let us just say for I is equal to 1 meaning the physical component is x, right, and j meaning 1, 2, 3 means you go from x, y and z, right. That is what you go. So, this del del x, so therefore, is x component of velocity, and j is also 1, which is this. Then this is still 1, right. Is that correct? Del del x, are we getting back? So, this should not be that, right. So, it should be y here, it just should be y, and this should be this and v dash. Is that correct? Is that correct? Right? Okay. So, essentially what then I think what we can let us just correct that then. This is fine, okay, except let us just say that j is equal to 1 and I goes from 1 to 3. I think that should be correct, and let us sort of rewrite this. Okay. Let us rewrite this. Okay. So, then if j is equal to 1, right, and I goes from 1 to 3. So, then it is del del x. So, x 1 is x, right, and I have I is 1. So, it is u, okay, and j is also 1, which is again u, and I have this. Okay. Then again I is equal to 2. So, del del y, okay. Then u will go from because j is 1. So, that will remain, which is u dash, and I again will become 2, which is v dash, which is this, right, plus x 3 is this, again j is equal to 1, j is equal to 1. So, the u dash will remain, and then what you will have here is this and this. So, now that works, right. So, now that works. So, if I write this equation such that this is, so therefore, I am going to write this total equation this way. So, that this is the condition we need to use along with it, along with this. Okay. So, then we get back the equations that I just spoke about. Okay. So, right hand side of course remains. So, what we basically did is we wrote out the left hand side of the equation. Okay. Right hand side remains this way. So, let us write out therefore the final form. Okay. What did we get? So, the final equation okay. So, this is okay. Let me write that down. So, left hand side turned out to be the mean of the total derivative of the velocity is equal to total derivative of the mean velocity time derivative, okay, and so this is the left hand side, right, and the right hand side is this. Yeah, that is also correct. essentially the mean value, right. So, this is essentially, so therefore, the as you can see, this is a time average. This is a time average. So, this equation is time averaged Navier-Stokes equations, right. So, this is a time averaged Navier-Stokes equation, right, and these are the terms that we get, right. Okay. Now, this is the term, this term, right. So, that becomes complex. This is the term which is complex, and it sort of brings on challenges with it. Okay. And I think this is where we will start next class, right, go on to that, and we will talk about, of course, the energy equation after that as well. But this is going to be the biggest challenge of the Navier-Stokes equation when you look at this point of view. So, now finally, to close, so we started out with the velocity. Essentially, this is the same velocity that you get for any field, but it's just that to study a turbulent flow, we have started writing out that velocity component in terms of a mean component of velocity and a fluctuating part. So, now that is how we are defining our turbulent flow, right, and that is an equation which will have to be plugged into the basic fundamental equation of motion. So, this is the momentum Navier-Stokes equation, right, and what we are doing right now is taking the definition of the velocity. We have decided for turbulent basic equation to see how far we it's worth, what are meaning. Right. So, that is what we have done. We have landed up with the final equation, and this, like I said, is laden with problems. So, let us come back and look at those, right, in the next. I think I will stop. Okay, thank you.